In this video, we are going to learn about the fundamental identities for trigonometric functions. Now, these are the very basic form of them. They all stem from the unit circle in some way. Now, again, I put at the top those unit circle formulas for how we read the unit circle, and we're using that same identity to come with a few more identities for trig functions themselves. So first, we'll start with the reciprocal identities. Now, we talked about this before when we first introduced these trig functions, but if you look over here, 1 over y, if you replace the y with sine, you get the reciprocal identity, 1 over sine of theta. And that can be written reverse-wise. Sine of theta can also equal 1 over cosecant of theta. That's what's nice about these reciprocal identities. You can write them twice or just write them once. It means the same thing. Secant of theta, 1 over x, gives me 1 over cosine of theta. And then we also know that cotangent and tangent are reciprocals, so we have cotangent is 1 over tangent of theta. Now the quotient identities come from these two unit circle formulas for y with y over x equal to tangent of theta and x over y equal to cotangent of theta. If y is sine and cosine is x, then it goes to show that tangent would be equal to sine of theta over cosine of theta. And cotangent of theta will equal cosine of theta over sine of theta, since cotangent of theta is equal to x over y. So using those basic little formulas up there. Now this next one may seem a little more complicated, but it's actually quite simple. The unit circle by definition is x squared plus y squared equals 1. And when we've looked at a triangle on the unit circle, you can kind of see a right triangle. And so we call these Pythagorean identities since we use kind of like Pythagorean theorem with the unit circle to get them. So I just reverse x squared and y squared in green just to show you that the first Pythagorean identity is y, which will be sine squared of theta, and it is proper to put the square in between the sine and the theta, just so people don't get confused that it's not sine of theta squared, it's sine of theta parentheses squared. So it's a proper notation. X is cosine, so we have cosine squared of theta is equal to 1. So they can combine to give you 1. It's a great way to reduce trig functions and expressions later on down the road. Now, there are 3 Pythagorean identities, and they're all easily found. One of the first ones you can find is divide everything by cosine squared of theta in the original Pythagorean identity, meaning we have sine squared of theta over cosine squared of theta plus cosine squared of theta over cosine squared of theta is equal to 1 over cosine squared of theta. What's nice about this is sine over cosine, we just learned earlier, is tangent. So we have tangent squared of theta plus cosine over cosine, which is 1. That will be equal to 1 over cosine, which would be secant squared of theta. So that's another form of the Pythagorean identity. And if I chose the other trig function, sine, to divide by, I would have sine squared of theta over sine squared of theta plus cosine squared of theta over sine squared of theta. Again, I'm just dividing the original one by sine squared equals to 1 over sine squared of theta. Simplifying this, I end up getting 1 plus cosine over sine, which we learned in the previous identity is cotangent squared of theta, is equal to 1 over sine, which we learned from the reciprocal is cosecant squared of theta. So again, 3 Pythagorean identities for the price of 1. Now let's put these in action. So now, given that sine of theta is square root of 5 over 5, and cosine of theta is 2 square roots of 5 over 5, let's find the exact values of the 4 remaining trigonometric functions of theta using these identities we just learned. Now we know tangent is sine over cosine. I have both of those to use, so I can rewrite it as sine of theta over cosine of theta, and now I can just substitute those values in. So I have the square root of 5 over 5 divided by 2 square roots of 5 over 5. So the square roots of 5s will cancel, the 5s will cancel, and I'm left with 1 up top in the numerator and 2 in my denominator for 1/2. So it's a very quick way for me to use trig identities to find the values of another trig function. Now, Secant of theta we know as 1 over cosine. And cosine of theta is 2 square roots of 5 over 5. So 1 over that would be the reciprocal, so 5 over 2 square roots of 5, which when I go to simplify, I can multiply the top and the bottom by the square root of 5, giving me 5 square roots of 5 over 10, which simplifies to the square root of 5 over 2. So very neat how you can do a little bit of algebra and really simplify that pretty quickly. Now cosecant of theta is known as 1 over sine, so I can put 1 over sine theta. And that's going to give me 1 over square root of 5 over 5, which again, take that reciprocal, gives me 5 over the square root of 5, which when I rationalize, multiply the top and the bottom by the square root of 5, I get 5 square roots of 5 over 5, which just simplifies to the square root of 5. Now for cotangent, I have two options to go about this next step. I can either use the quotient identity, cosine over sine, or since I now know tangent, I could also use 1 over tangent of theta. But for the sake of using as many colors around here as possible, I'm going to use the quotient identity. So I know that it's cosine of theta over sine of theta, which gives me 2 square roots of 5 over 5 over the square root of 5 over 5, which again, the square roots of 5s will cancel, the 5s will cancel, and left with just 2 over 1, which is 2. Which again, double checking, that is the reciprocal of 1/2, which makes sense with the reciprocal identity. Now another way we can use these identities is when we actually know the angles and we want to evaluate some expressions that look like something might be able to simplify or reduce. So down here, tangent of 20 degrees, we don't know how to find that exactly without a calculator, but we can still evaluate this expression without using one. Because I know that sine over cosine is tangent. So this can become tangent of 20 degrees minus tangent of 20 degrees. And tangent of 20 degrees minus itself will yield 0. So that's a way we just simplified that without a calculator. And I bet we did it faster than it would take to input that in your calculator, which is very nice. Next up we have sine squared of pi over 12 plus 1 over secant squared of pi over 12. Now, using the reciprocal identity, I can replace 1 over secant squared just with cosine squared, since that is its reciprocal. Even though it wasn't listed here, I know I can reverse their locations and it still means the same thing. Now, I have sine squared of pi over 12 plus cosine squared of pi over 12, and if those angles are the same, then that identity should just yield 1. And it's very nice to use these identities. Once you get used to them, you can kind of use them to very quickly reduce the size of some of these expressions. And now you know how to use these fundamental identities in creative ways to evaluate these expressions.